Parvez sir.
Yes, sir. Yes, sir.
I think we will start.
Can you start?
They'll join back, and you already introduced yourself.
So let me introduce myself again. So I am Parvez Shaikh, and I have been working in IT industry for around 22 years. And my major specialty is on databases, big data, Hadoop, and machine learning. And I'm here actually to take a session on dimensionality reduction. So I would like to have a small introduction from all the participants, if you don't have any problem. So we'll start with Rathod sir.
Oh, I am Dr. Surendra Rathod. I am from basically electronics department. I
Yeah.
am the coordinator of the workshop.
Oh, that's great. Yeah. Till now, like I
Welcome,
was
sir.
just communicating on the messages and all
Yeah,
those things.
yeah,
So
yeah,
yeah, the first
yeah,
time I've heard you, so it was nice. It is nice actually, like hearing you.
yeah.
Next, I think Miss Pallavi Thakur. Madam, can you give us a brief introduction about yourself?
Hello, sir. I'm Pallavi
Yeah.
Thakur. I am
Yes.
assistant professor at S.P.I.T. in MC
Mm-hmm.
department. I
Okay.
actually wanted to introduce you, but you introduce yourself.
Mm,
I'm in organizing committee of this AICT approved FDP.
great to be here.
Yeah, and I'm very much interested because my area of interest is data science and machine learning. So I'm
Okay.
very much interested in the topics that you're going to cover today. Thank
Good.
you.
Very nice. Miss Apeksha. I think Apeksha, can you hear us? Okay, we'll move to Dr. Chetna Kamlaskar. I think you guys can hear me, right?
Yes, sir.
Yes.
Okay. Um, Dr. Kranti Vittal, can you introduce yourself? Cool. She has sent a message. So, yeah. Next is Dr. Nirbhay Chaube.
Yeah, good evening. Here
Hi,
is
good evening.
nice to see you. Here is Dr. Nirbhay Chave. I'm Dean of Computer Science, Ganpat University, Gujarat. I
Oh,
have
great.
overall almost 20 years experience in teaching and
Okay,
industry. So I'm
great.
very much interested to, in fact, learn something more about your talk. I'm in Python using PCA and SVA that you have mentioned.
Not a problem. It's a great to have you here, sir.
Yeah,
Uh,
pleasure same here. Thank you.
uh, so, anyone else would like to introduce yourself? Like, I think it's a big list. It's actually growing on. So, like, I'm finding it a bit difficult to actually figure out one person and ask them. So, one by one, can you just like, if you want to give a brief introduction, like, I don't want to delay the session.
Okay, hello sir. Good
Yeah, hi.
evening. This is Harshil Kanakia from MCA department at S.P.I.T. and I'm
Okay.
in organizing committee as well as I'm a participant for FDP1, that is Foundation of Data Science. And my area of interest is machine learning, sir. So I
Okay, good.
wanted to learn many things in this workshop. So thank you, sir.
Yeah, machine learning is actually a vast subject, and it
Yes, sir.
actually
Yes, sir. I'm still learning many things in machine learning, sir.
okay.
Yeah.
Someone
Thank you, sir.
else? Okay, so let me like just start with the session. Like we'll start with the topic. Okay. So let me share a PPT with you guys. Okay. So you can see the screen, right? Can everyone see my screen? Can someone
Yes,
tell me, like,
yes,
can
yes.
any one of you
Visible and
volunteer,
audible.
like, yeah, little bit of audio problem. Now you can hear me. So, can someone actually volunteer, like when I ask some question, like whether you can hear me or not? So if they can reply, it will be better for me actually. At least one of the guy can volunteer.
Harshil, you can do na?
At least one of them like can volunteer, like no, at the time when I ask some question, because I don't know like what's happening basically.
Yeah.
Okay, so let me start with dimensionality reduction. So let me give you a brief, like what do you mean by dimensions? So let's say like I have a data set. Let's say I have a small data set of a housing company in the locality, like a housing data set, wherein like I have number of rows which actually represent my apartments in the locality. Let's say this is apartment 1, this is apartment 2, this is apartment 3. Okay, and I have various columns in my data set. So let's say like this is a square feet area, this is like number of bedrooms, you can say. This is whether the premises have a swimming pool or not. Let's say pool. And lastly, like I have a price column. So what are dimensions? Dimensions are basically the attributes of your data set. So these attributes are called basically dimensions. Okay. So in machine learning world, these are also called as features of your data set, because this actually represent the feature of the apartment. So what's the square feet area, whether how many numbers, like two bedrooms are there. So these are my features in my data set, features of my data set. Lastly, it is also called as variables. So you can actually, people call it as variables also. So now let's say like I have a model which I have trained on and which actually predicts the price of the apartment based on these features, rest of the features, let's say three features. So these three features are called as input features. What are they called? They are called as input features. Okay. Or they are also called as predictive features. We call them as predictive features. Okay, and the price column which actually my model predicts, it's called as a output feature, or you can call it as a target variable. So these are the terms which are used for dimensions in my data set. Okay, so today we will be discussing like what dimensionality reduction is and how we can deal with highly huge dimensions in my data set. So the agenda for this particular slide is basically we will be discussing the need for data dimensionality reduction and what exactly is data dimensionality reduction and what are the techniques of data dimensionality reduction. Okay. So basically in the machine world, in basically a machine world, what it is said that like if you provide a lot of informations, like the more information you actually provide to your model at the time of training, it will actually perform, it will give you a better performance. But in real world, in real life, it's not that true. So there is particular, like there is a particular point in my graph, like you can see, like if I draw a graph of like number of variables to my performance matrix. So what you can see that after particular point, like after number of dimensions, what happens is that my performance actually goes on reducing. Okay, so this problem actually of having more dimensions, a huge number of dimensions, so there might be like around thousands of 10,000 of dimensions in my data set. So this problem is called curse of dimensionality, which Richard Ernest Bellman has referred to as. Okay, so what exactly the curse of dimensionality is, I will just discuss that first. Okay, so one of the curse of dimensionality is basically complexity. So you can see from this particular diagram. So let's say in my diagram one, like I have a single line. Okay, so this single line is of, let's say, 100 yards line. Okay, now what happens, like if I place a coin somewhere on that particular line, it will be more easier for me to actually find that coin. I can start walking from one end of the line to the other end, and I can actually find that coin. Okay, so now when I increase the dimension of my space, let's say from a single line, I move to a square of 100 yards. Okay, so what will happen? Like if I place a coin somewhere in the square, it will be a bit complex to actually find that particular coin in my dimension, right? So comparatively, what it was there, what it was there in finding a coin on the line, single line, it will be a bit difficult for me to actually find in a square. So let me go one step further. Okay, let me increase my dimension from a space to a cube. So let's say I have a cube. If I place a coin inside that cube, it will be more complex than finding a coin on the line and the square. So you can see from this particular diagram, as the number of dimension increases, the complexity actually increases. So this is actually one of the curse of dimensionality. So the example where we have this kind of complexity are like image processing, where you have like a lot of dimensions, like each pixel actually becomes my dimensions. So these are the examples of like complexity of my basically complexity curves of dimension of what we are discussing right now. Okay, so another curse of dimensions is like redundant features. So you can see from this diagram, like I have trained my models like model M1, M2, M3, M4 till M7, right? So in this particular model, model M1, I have provided only two features to actually train on. Okay, and similarly on model 2, I have trained on 4 features, and model 3 I have trained on like 8 features, and so on. So my model M7, it has been trained on like 1,000 features. So theoretically speaking, like as I provide more number of features, more number of dimensions to my model to actually train on, the accuracy of my model should increase, should go on increasing. But in real life, in real world, basically what you will see that at particular point, let's say when I actually check the accuracy of my model M1, it will be a bit lower. And when I check my accuracy of my model M2, it will be a bit higher than my model M1, because I have provided 4 dimensions or 4 features to my model to actually train on. So as I go on till my model M5, I can see that my accuracy level has gone till like, let's say, 90%. Okay, so after that, like if I check my accuracy level of model M6 and M7, I will see that it has reduced, like it has gone to, let's say, 80%. So basically why this happens, like as soon as I go from my model M5, from M5, like where I have given only 12 features to train on, if I provide one more feature, let's say 13 feature, the accuracy of my model actually decreases. So how does this happen? Let's say, let me give you an example. Let's say I have a model which I have trained on. Okay, and let's say I have trained my model to actually predict whether the object is a ball or not. So let's say my model predicts whether the object is a ball or not. So over here in this particular example, I have trained my model on these 4 features: whether the shape is spherical or not, okay, whether the object is eatable or not, whether I can play with the object, whether the object is red in color. So what it happens basically when I take this model to actually do a prediction. So let's say I gave my model an orange. Okay, so it will check whether the shape is spherical. So it's spherical. So it says it's a ball. Then it moves to the second feature of the object. It says whether it's eatable. So it's eatable. So over here it predicts that it's not a ball. So in this scenario, what happens basically, my model has predicted correctly that this is not a ball. Okay. Now let's say I am giving my model a second object with which is like a ball, but it's white in color. So what my model actually does is basically it checks whether the shape is spherical. It says yes. Whether it's eatable. It says it's not eatable. So it's a ball. Okay. So whether I can play with that object? Yes, you can play with that object. So it says it's a ball. When I move to this particular feature, so it checks whether the object's color is red or not. So now the object color is white. So what it predicts, it says like, no, it's not a ball. So it has actually predicted incorrectly. So you can see from this particular example that as you give only three features to your model to predict on, it will predict correctly, right? So as soon as you add one more feature, that is like the red color, the model started predicting inaccurately, right? So the model actually gets confused over here. So basically, this is one of the curse of dimensionality, like redundant features, the features which are not useful, which are irrelevant features. It confuses your model. Okay. So from these particular slides, what we have observed that the more number of columns or more number of features you have, it's not guaranteed, it's not mandatory that it will my model which has been trained on higher dimensions will be more accurate or the performance will be greater. Okay. So as the dimension increases exponentially, the complexity increases, right? That's what we have actually seen from example one. And irrelevant features like the red color feature which you have seen in the previous example, like it says that irrelevant feature reduces the accuracy of the model. And lastly, the last point, as the dimensionality increases, the computational cost also increases. So what does this means basically? Let's say you are training your model on like 10,000 dimensions, okay? And let's say like you have million rows, like a million samples in your data set. So training on these particular big data problem, the model, if you'll start training, it will need high computational power like a GPU or a high memory. And assume that if you want to keep on tweaking your parameters of the model or training the model, like if you're tweaking every time and every time you are processing, it will like it will consume a lot of time to actually train and lot of infrastructure cost. So these are basically the observation which we have seen from the previous slides, and this is why we need data dimensionality reduction process to be done on your data set. Okay. So what is the dimensional reduction? So basically, it's a technique to actually filter out significant features. So what do you mean by significant features? Features which are important for your data set to actually train your model. So you will actually filter out those features. And it's a technique to reduce the dimensions without losing the information. So what does this means is basically while filtering out the irrelevant feature, you should not lose the important information which you have to provide to your model to run on. Okay. And lastly, a technique to filter irrelevant features to increase the accuracy. Irrelevant features, as we have seen, we have to filter out like the redundant features, the features which are very irrelevant. So we'll talk about techniques of dimensionality reduction. So one of the technique is feature selection. So in this feature selection technique, what you do, we select some of the features from all the features which you have in your original data set. So there are two methods actually for feature selection. One is threshold based method and one is variance based thresholding. So I'll just explain a bit on threshold based method. So let me take an example of like I have, let's say, uh, two documents. Let's say I have document one, which has words like I am learning machine learning, right? And second documents, let's say I have words in them saying I am learning Python. Okay. So in bag of words, what happens is all my unique words in all the documents that become my dimensions, right? So basically, let's say I have my dimensions are now I am learning ML and Python, right? This is my, these are my, now becomes my dimensions, right? So my data set will look like this, right? So let's say my first document, document number 1 has word I. So I will mark it as 1. It is having M. So I will mark it as 1. Similarly, learning ML and Python is not there. So I'll mark it as 0. Okay. So in the second document, I have the word I am learning, and I don't have machine learning as a word in my document, and I have like let's say Python in the document. So if I provide these data to my model to learn on, what will happen, like my model will get confused because it will bias towards these three words because these are like almost present in both the documents, and it might categorize both the documents into one single category. So basically I want to categorize whether the document belongs to ML category or whether this belong to Python category. So, but if I give this particular data to my model to train on, it will get confused and it might actually categorize both the documents to a single category. So in threshold based feature selection, what we do basically, we give some kind of cutoff. We say like, I want only dimensions which actually occurred only once throughout all the documents. So what will happen, like I cut off these features, these dimensions, okay, and I just consider only these two dimensions to actually train my model. So in this case, my model will be like very much clear, like okay, if ML is coming, then it belongs to category machine learning, and if Python is coming in the word, then it's in the document, then it's a it falls under Python category, right? So this is basically uh, threshold based method. Are you people getting it? Yeah, can I have some reply?
Yes, sir.
Okay, so should I move ahead? Cool. So next method of feature selection is variance based thresholding. So what do variance based thresholding means? Basically, you are filtering out the data, the feature which has low variance. Let's say I will give you the same example of like housing data set. Okay, let's say I have a housing data set and I have one of the feature as number of bedrooms. And if suppose, let's say all the apartments in the locality has two bedroom flats only. Okay, those are having all are having two bedrooms. So what will happen, this data doesn't have any kind of variance. So what I can do in a variance based thresholding, I can filter out these particular feature and I can give remaining features for my model to actually train on. Okay, so this was a feature selection method wherein like you select some of the features from all the features. Now there's a other method called other technique of dimensionality reduction, that is feature extraction. So what exactly feature extraction means? So feature extraction basically means that you generate a new features from the combinations of your old feature. So basically, let's say like you have let's say my data set has like 10 features, F1, F2, F3, F4, and so on till F10. So what you basically do is like you generate another 10 features out of these features. So let's say I have, let's say I'm generating a new feature called NF1. Okay. So what I can do basically, I can give some weighted average to this first feature of mine. And let's say I gave some weight of, let's say 3.5 or something like that. And comparatively, I give lesser weights to all these new features. Okay. And similarly, I can construct another feature NF2 with giving some higher weightage to my original F2 feature and lower weightage to rest of the features. So so on, I go on creating like 10 features out of my original 10 features, and I can see which are more relevant features out of these 10 features which I have constructed out of my old feature. So I can take those features and I can reduce the dimensions. So basically, let's say if I find out that like first two features which I have constructed, which I have generated from my older feature, those are only relevant. I can just take those features and I can train my model and I can use for a data explorer EDA part also. Okay, so this is called feature extraction. And feature extraction usually basically we have two type of feature extraction. One is linear feature extraction and one is non-linear feature extraction. So in our current session we will be actually concentrating more on linear feature extraction. It's widely used in the industry. Okay, so some of the linear feature extractions are principal component analysis that we'll be doing right now, and LDA, that is linear discriminant analysis, and we'll be going through singular value decomposition. So all these features will be like looking into details, and we'll be like actually coding in Python, and I will actually show you, give a live demo like how you can code from scratch all these algos. So let's move to principal component analysis. Okay. So let me just give you brief about like what principal component analysis is. Okay. So let's say like I will take the previous example which I have given. Let's say I have feature F1 till F10. Okay. Let's say F1, F2, F3 till F10. Okay. So I am generating my first new feature by giving some weightage, some higher weightage to F1 and relatively low weightage to all the other features up till F10. So this feature will have higher weightage while constructing the new feature. Similarly, I will construct the feature NF2 which has higher weightage to F2 and lower weightage to rest of the other features. So similarly, I will go on computing. So in PCA, what we do, we basically generate those many numbers of principal components, the number of dimensions, whatever we have, that many number of principal components we actually keep on generating. So since I have 10 features in my original data, so I will generate 10 new features in my 10 new principal components in my in my piece, 10 new principal components I will generate. So now what PCA does, basically PCA does some changes to this particular feature, let's say delta T, and it sees like what impact does this particular feature has on the output variable or like has on the output. So basically, let's say this has a variance of, let's say, 0.2. Okay. Now, similarly, it will keep on tweaking and it will see what exactly each principal component has what impact on the output, and this is actually computed by seeing the variance in the data set. Okay, so basically like variance in the feature. So let's say my second feature which I have generated has the variance of, let's say, let's say 0.3, and my 10th feature, let's say it has a high variance of like 0.70. Okay, so now what will happen, basically my 10th feature which is having a variance of 70%, that will be my first principal component. So basically it means like it has 70% of variance in it. Okay, and my second principal component will be NF1 because it has 20% of variance in it, and rest of the features, let's say they have like 0.05 variance or something like that. Okay, so what does this means is like if I consider only two features, NF10 and NF1, what does this means is basically if I consider these two dimensions, then these two dimensions are enough to represent my whole data because they have 90% of the variance. and that's how it makes our life easier, simpler, actually, like to do a analysis or to do EDA. Because let's assume like if we have 1,000 dimensions, and if you want to do EDA on these 1,000 dimensions, what you will do, you will like plot those many numbers of scatter plot and all those things, and it will be a bit difficult to actually explore your data or analyze the data, instead of like exploring on a two-dimensional or a dimensions like around 10 or 20 dimensions. So this is how like PCA makes our life easier. Okay, so so basically, as you know, like PCA is a technique for dimensionality reduction. Okay, and as I've told, like PCA makes exploratory data analysis easier and actually make predictive models easier. Basically, like providing less of the model, so it will be like it will get processed faster, and it will be like more accurate. And PCA helps in preserving as much of data variation as possible. So as you can see, like my principal component, which has the high variance, actually PCA retains those dimensions, and actually those are then my final dimensions which I provide to machine to learn on. Okay, and PCA helps in identifying correlation and patterns in the data set. So what does this means basically is, like, let's say if you have two dimensions which are like very highly correlated. So what happens basically when you provide these dimensions to the machine to learn on, what it will happen is it will be biased towards those two dimensions. And if those two dimensions doesn't have any impact on my output variable, then it's really useless to actually provide those two dimensions to the model to learn on. And if I provide those dimensions, then my model will be actually biased towards those dimensions. So we have to make sure like we remove highly correlated dimensions from our data set to actually give it to a machine to learn on. Okay, so we'll just see step by step like how PCA is calculated. So the first step for machine learning, basically you can say standardization of the data. This is actually like used for uh, every machine learning process. So I'll explain you in the slides further, like how to do standardization. Then after that, like you have to compute your covariance matrix. Then from that covariance matrix, you calculate eigenvectors and eigenvalues. And eigenvalues actually helps us to find out the principal components which has high variance, and then you compute the principal components out of your eigenvectors and eigenvalues, and based on that principal components you actually reduce the dimensions of the data. So let's go to step number one, that is standardization of data. So what is standardization? Standardization is nothing but scaling your data in such a way that the variables or features actually like fall within the same range. So uh, just look at this particular example. Let's say I have a data set of a movie, okay, in which I have a rating column, I have number of downloads. Okay, so as you can see from the diagram, like the rating column is between the range of 0 to 5, while my download ranges from 100 to 5,000. So if I provide this particular features like to my model to actually train on, what will happen, like my model will be more biased toward the feature which is having high range of values. Okay, so basically what will happen, like my download number of downloads will have more impact on my model than the rating column. Rating actually like has a value from 1 to 5, but my number of downloads are basically like much more higher. So what we do basically, we actually standardize our data, standardize our features, so that both the columns, both the features actually lie in the same range. Let's say in some decimal points, let's say from -1 to +1, or some smaller ranges wherein like they actually fall in the comparable range. So what exactly we do, like this is a kind of standard scalar process wherein we actually take the value, separate it by the mean value of that feature, and divide by the standard deviation. So this actually gives me the Z score of the particular feature, and that will actually lie within the same range. So basically, like if I talk about like a normal distribution, so my Z score basically most of them lies from 0 to 2, right? So basically, these two features will get standardized, and it will be like it can then be provided to my model to actually learn on. The second step is like computing the covariance matrix. So as you know, PCA helps you to identify the correlation and the dependencies among the features in the data set. So we have to, as I've told, like we have to remove the variables which are highly correlated to each other unless it's your predictive variable or your target variable. So if the predictive features are highly correlated to each other, then your output will be biased again to those particular variables. Like I said, it's very important to find these variables because they contain very biased and redundant information, which will reduce the overall performance. So mathematically, the covariance matrix is a P by P matrix, right? Where P denotes my number of dimensions in the data set. So for example, if I have 10 features, so my covariance matrix will be 10 by 10 matrix, right? So each entry in your matrix will actually represent the covariance of the corresponding variable. So consider a case where I have a two-dimensional data set, like here, let's say my dimensions are A and B. Okay. So if I have a two-dimensional data set, my covariance matrix will be 2 by 2 matrix. Okay, so covariance of a comma a will represent the covariance of a variable with itself. Now this is nothing but the variance of the variable in itself, and covariance a comma b will actually represent covariance of a with respect to b. And because this covariance is commutative, covariance of a comma b and covariance of b comma a will be same, right? So there are three takeaways from this covariance matrix. So basically, first is like how codependent these two variables are. So basically, like if let's say my covariance of a comma b is, let's say the covariance of a comma b is +3. So what happens is that what this means is that what this denotes is that that a is highly related to b. That means like a is directly proportional to B. So this is called positive covariance. And the negative covariance means that A is indirectly proportional to B. So as A increases, B decreases, right? So these are the three takeaways from this particular slide. Okay. So from this covariance matrix, what we do, we basically calculate eigenvectors and eigenvalues. So eigenvectors and eigenvalues, as you know, are the mathematical constructs that must be computed from the covariance matrix. Now, the reason why you need eigenvalues and eigenvectors is so that you can determine the principal components of the data set. Now, at this point, you might be wondering what principal components are, right? So just uh, like simply speaking, like it's a new set of variables that are obtained from initial set of variables, as we have discussed earlier. So they actually compress and process most useful information that was scattered among the initial variables. So let's say like you had initially you had 50 variables in your data sets. Okay, so that means like your information was scattered around those 50 variables. Now let's say you generate 5 principal components out of these 50 variables. So what does this mean? Like you have actually collected all the information in these 5 principal components. So, and as you know that all information are not useful information. When you are forming your predictive model, some information can be ignored because having extra redundant information will only increase the complexity of your model, and it will result in low accuracy overall, right? And performance will be reduced because you are performing unnecessary computation which might affect your final output. That's why you have to make sure that your principal component should have essential data in them. So if your data set has 5 dimensions in them, then you have to form 5 principal components. So initially you have to start by forming same number of principal components as the dimensions are there in your data set. So what you do is like your first principal component will have the most info, will have maximum possible information. So and your second principal component will have uh, uh, second most important information, and so on, right? So when you do this, you know that if you arrange your data, or if you arrange these values like principal components in the descending order, so the first principal component will be of a high significance, will be having most important information in that first principal component. Okay, so now where exactly these eigenvectors and eigenvalues actually fall in this whole process? So I assume that you have a basic knowledge about eigenvectors and eigenvalues. Now let's say these are actually two algebraic values, and they are computed together in pairs. So basically, for every eigenvector there is an eigenvalue. The dimension in the data will tell you how many eigenvectors you need to calculate. So let's say if I have like 5 columns or 5 features in my data set, so I'll be computing 5 eigenvectors and their respective eigenvalues. That exactly, and these eigenvalues are used to identify where in your data you have the highest variance. So basically, if you have the eigenvector which is having a higher eigenvalue, that signifies that that particular vector has a more variance in my data set. So this is how eigenvalues and eigenvectors actually helps us in finding the principal components. Okay. So now moving to step number 4, computing the principal components. So basically, and now once like you finalize the eigenvectors and eigenvalues, you can just order the eigenvectors with the highest eigenvalue in the descending order of the highest eigenvalues. Okay. So in this manner, what you do is you have ordered list wherein the first eigenvalue will denote your first principal component. So when you arrange your principal components in the descending order, so the higher significant principal components will be on the top, and you can just remove the lesser significant principal components from the list. Okay. Also remember that in this step you form a matrix known as feature matrix, which basically contains all the significant data variables or all the significant principal component that possess the maximum information about the data. So this is everything you need to know about principal components. Okay. And now let's go to the last step. So last step, like with those principal components, you actually reduce the data. So basically, more relevant features, more relevant dimensions will be kept for the future reference for actually training your model, and the less relevant features, less relevant principal components will be removed from the data set. So when the dimensions in your data set are much lesser, it makes your job like 100 times easier for you, especially when you are dealing with your large data set, and that usually the case in machine learning and deep learning. Okay. So let's move ahead, and we'll go towards a coding part. Like we'll have a live demo of a code. Okay. So Mm, I want to ask everyone so I have already pre-coded and I will be explaining you line by line the code, and I want you guys to actually write a code, whatever code I have actually given you, and I think after I execute the line of the code cell by cell, I will ask some of you to volunteer and explain me what I have actually explained. So, do you know about Google Colab? Anyone? So I can. So someone told me like give us link of your Colab notebook. We will make copy of it. So Okay, you want me to do that way basically, or you want to write the code? So it's not. I don't think so that the code is much complex. So I think I can explain you line by line. I can give you time in between, and you can write the code. So it's not that complex code. Are you comfortable with what I am telling you right now? So okay, wherein I can share my Google. I don't have on the collab. Let me put it on the collab. Just give me a second, guys. I'll just share it. Just one sec. Can you just see like you have access to this file? Can anyone reply to me? No. I have to actually provide email address, right? Can someone give me the email address? Like I can just share with one of them and they can share it on the.
So, can I say something?
Yeah, yeah.
This make a setting that those who are having a link can access it, so it won't be restricted.
Where exactly that is?
Get a link.
Change.
Yes, yes, change.
Okay, got it.
Anyone with the link can edit, because we can make a copy of it at our end, and we will not
Okay.
able to change. Like we won't be working in your copy of the notebook. We will work on our copy of the notebook.
Fine. So I have done that. Can you just see?
Yes, I'll just check it.
Yeah.
Yes, sir. Now I can access it.
Okay, so everyone can access them. All right.
Yes, everyone can access. Thank you, sir.
So, okay. So, I'll just open my Jupyter notebook. Okay. So in the first cell, as you can see, like I am importing my libraries, like Seaborn library, which I'll be using to actually import the data set. So Seaborn has like inbuilt libraries, inbuilt data sets, which I can use for my learning purpose. Okay. Then you have like NumPy library, which I'm importing because I want to do some operations on array, which NumPy actually helps in doing that. And third, I'm importing pandas, wherein like I can create a data set. I can load the data set into a data frame, and I can do any operations on them. Then I am importing a library of matplotlib pyplot, which is basically used for plotting my graph. Okay, so these are the aliases I have given to each of the libraries. So basically, I think you might be knowing, like if you give an alias, you don't have to actually type in the whole library name when you are referring to any of the object in the library. Okay, so I'll just run this particular cell import. Okay, so right now, like what I am doing, basically I am like loading a data set. Okay, this is a Seaborn library, from where I am like loading a inbuilt data set of a iris flower. So this is the most commonly used data set, which you will find on the internet or various other places where which people actually use for actually training purposes. So this command will actually load my iris dataset into a variable called iris data. Okay, so you can actually give whatever name you would like to give. So this will load my dataset into a iris data variable. Okay, now let me do some EDA part on my dataset. Okay, so let's say I am doing a iris data dot head. So it will list down top 5 records of my data set. Okay, so as you can see, this data set has has a feature sepal length, sepal width, petal width. So it has 4 features and a species, which is the fifth feature, which is basically like what I can do. I can actually provide these 4 features to my model to actually train on, and it can predict the species out of these 4 features, right? So you can see like in the species, like there are species of flower like setosa. There are 3 species of flower. So we'll see later on what are the species of flower. Okay, then you have this. I'm calling a shape property of the iris dataset. So what it does basically, it actually prints me the shape of the iris dataset. So it says like I have 150 samples, 150 records in my dataset, and I have 5 columns, that are 5 dimensions in my dataset. So it's a 150 by 5 matrix. Okay, so these are like pandas method and properties. Basically, this head, this shape, these are pandas properties. Okay, so now let's find like what are the unique species I have in the data set. So what basically this does is like it will give me the unique values in my species column. Okay, so as I can see here, like I have 3 different species in my data set, that is Setosa, versicolor, and virginica. Okay, so these are my 3 species of flower in my data set. Okay, so up till now, can someone take an initiative and explain me like up till now what I have explained? Can someone self volunteer? I think I have to catch hold of someone and Just one second. Okay, can someone explain me like what I've explained till now in a just brief 1 or 2 lines? Apeksha, can you explain me?
Yes.
Yeah.
Basically, you have imported the libraries like
Hmm.
C1 library, NumPy library, pandas, and matplotlib.pyplot. We have
What
given
does
the analysis.
matplotlib does?
It's for the plotting.
Okay,
According to
cool.
me, I don't know in detail.
Okay,
Uh,
cool. So it's used for plotting the graphs and all. Like
yes.
we'll see
Yeah,
later
according
on.
to me, for that it is for the graphs. That's the usage of that I know.
Yeah. So what does this particular line does?
In the first code snippet, you have created the analysis of each of the libraries so that by making usage of them, we did not
Yeah.
write the entire name of the library, and it will help us to go faster.
Okay,
In the
cool.
second snippet, you have loaded the dataset named as Iris.
Where is this iris dataset coming from?
I think it is coming from internet because we have not
Uh,
uploaded anything. So
no, no. So it's
then,
not coming from internet. It's basically I'm using sns.load dataset. So this
okay,
C1 library has inbuilt
okay,
datasets. Okay, so I'm
okay,
loading that dataset, the inbuilt dataset of C1 library into my variable iris data.
okay.
Okay, yeah, good.
I was not
Going
aware
good.
about
No,
that
no,
it is
going.
in build.
Okay, okay.
Thanks
Going
for
good.
letting
Going
us.
good. Yeah, yeah.
In
And
the third snippet, you have read the first 5 rows of that particular data set using the head function.
this is the head method, yeah.
Yeah.
So basically, if I say like 10 over here, if I don't pass the number, it will return me 4 records, but 5 records. If I pass a number, if I say 10, so it will return me 10 records. Okay. So this is the function of head method. Cool.
Actually, sir, we have used this head method, shape method earlier. We
Okay.
all have
Okay.
used it.
Okay. Okay.
In the code snippet, you wanted to know the dimensions of the data set. So you have used the shape command, which tells that
Hmm.
there will be 150, there are 150 rows and 5 columns.
Cool. Cool. Okay. Okay. And this just taking the unique species in my, I'm just checking what are the unique species in my data set. So I got setosa, versicolor, and virginica. Okay, so now let's move towards PCA. Okay, so these we have done EDA about our data set. So we have seen the shape, we have seen number of records, we have seen what are the unique species I have in my data set. So right now we'll go to the first step of the data set. Can someone tell what's the first step of PCA, which I have explained in the slide? Uh, I will just ask Harshil Kanakia. Mr. Harshil Kanakia, can you just tell me that do you remember like what was the first step in our PCA process? I think Harshil is not audible. I will move ahead. I will ask Dr. Chetna Kamlaskar. Can you just let us know like what was the first process we explained in the PDF? Okay. Let me just tell you, like the first process in the while doing the PCA was like doing a standardizing the data set, right? So here basically in our data set, like mostly like all the features, all the values in the feature lie in the same range, more or less the same range. So it's like it's not of use, but like even though I'm like doing it over here to show you how you can do the standardization of the data. So basically before that, what I have done basically is I have label encoded one of my categorical feature. So let me explain what categorical features are. Okay. So let's say I have, so in my data set, I have petal length, petal width, Okay, I have width, I have sepal length and sepal width, right? Sepal length and sepal width, right? And I have a column called species. So as you can see in my data set that all these width and height columns, they are basically a numerical column. Okay, and this species, like they are having characters in it, like setosa, versicolor, and virginica, right? So when I provide anything to the machine to learn, to my model to learn, I have to convert this into a numerical category, numerical column. So basically what this means is like I have to label encode them. So I have to give some kind of numeric labels to all these values. So basically, like let's say for setosa I will give a value 1, for versicolor I will give value 2, and virginica I will give value 3. So this is how I do label encoding of my feature. So just remember, like in machine learning, whenever you are like providing a data, machine learning doesn't understand the character data sets. So whatever you have to give, you have to actually give them in numerical manner. So this is what actually I am doing. So basically, what happens is like I am just separating out my input features and output features. Okay. So what I am doing basically, I'm like calling I'm using a drop method of my pandas library, and I'm saying like drop the species column from the iris dataset. So my iris dataset has had sepal length, sepal width, petal width, and species, right? So what it is doing, like in my x variable, it's like dropping the species column from the iris dataset and just keeping only these four columns, these four input columns. So these are my input features. So X has all my input features and Y has my output feature. That is basically the species column. So I am just taking filtering out species column into my variable Y. So this is how you basically do slicing in pandas. Okay, so here axis 1 means column, and if you give axis 0, it's row basically. So you have to specify like from where you want to remove the row or the column. Okay, and this basically this line of code, like I'm importing label encoder. It's a inbuilt it's a like inbuilt method, like inbuilt method in sklearn pre-processing library, wherein it will actually label encode your categorical column, and it will return you those columns. So basically if you'll see this, I'm just creating a object of label encoder, and I'm calling a function of that label encoder at fit underscore transform. So what this does basically, this actually learns on the data set and then it transforms the data set. So basically you can call first, like it can be done in two ways. Like you can first call the fit method, then you can call the transform method. And the second way is like you just call fit and fit underscore transform. It will do both the things. It will fit the it will learn on the data set and it will transform the data set. So it will transform from like character, like categorical data set to the numerical data set. So this is what I am doing. So remember the first step in PCA, we were doing like we were normalizing the features. That is like scaling the feature to basically have all the features in the same scale, so that it's in the comparable units. So what I'm doing over here, I'm like using a standard scaler, which actually gives me the Z score. So what I have explained in the PDF earlier. So this is what this particular method does. So basically, I'm creating an object SC of standard scalar, and I'm like doing a fit and transform, calling the fit and transform method of that standard scalar object and passing the parameter, the data, the input features. So one more thing I want to specify, basically PCA is unsupervised learning. What does that means basically? PCA doesn't require the output features to be present. Like while doing a PCA, we don't need the output feature. We only need the input features. So it's a kind of unsupervised machine algo. Okay. So here I am doing, I am basically standardizing my data. I'm doing like scaling of my features. So I'll run this particular line of cell. It has run. So let's just check the top 10 records in the X variable. So I have scaled the variable. I have scaled the features. So you can see like these features, the sepal length, sepal width, and petal length and petal width has been scaled to like really small numbers, like from probably it will be like from -2 to +2. So this is basically a step to actually standardize the data. Okay, so can someone volunteer like to explain this? Can someone apart from Apeksha can volunteer? Uh, Vikas Gupta, can you just, Mr. Vikas Gupta, can you just explain me like what I have explained?
Hello.
Yeah, yeah, tell me.
Yes, sir.
Yeah. So I want to explain this particular cell like na, or how I have
Uh,
explained it.
so first we have separated the input and the output quantity. Like in the first row, you have written that x equals to iris data dot drop. So we are
Mhm.
dropping all other columns. We are only keeping the first column
No, no,
in
no.
this.
It's the other way around. It's the other way around. So we are dropping the species column and keeping all other columns.
Oh, okay, sorry. So and then the remaining columns are then saved in y variable y.
No,
And
so here it is like I am dropping the species column from my data set, iris data set, and the other rest of the other columns, these four columns, I am storing it in X variable. Okay.
okay.
Okay. So what does this do?
So it will save the further the species column into variable y.
Yes, that's great. Okay. Can you explain me what label encoder does?
Label encoder will basically it is generating an object there, means this function is basically assigned to this variable GLE.
Okay.
And
And what does this is used for basically? If I am calling the fit and transform method of label encoder, what does this do?
I used it. Uh, so
This
that
can
I
someone help?
forgot.
Can someone help from the group? Like someone else can take it from here. I think Gauri Shankar, Mr. Gauri Shankar, like can you take it from here? Like what Vikas Gupta has explained. Okay, so this basically transforms my categorical column into a numerical column, right? That's what I have explained, Vikas Gupta. So basically, I have this species column wherein like I have categories. I have like categorical. It's a categorical column. It has characters in it like Setosa, versicolor, and virginica, right? So it actually gives some numerical value to these categories. So all the values where there is Setosa, it will replace it with 0 or 1. Okay, and versicolor, it will replace with 2, and virginica, it will replace with 3. So that's what it does. Okay, so
Okay.
uh, so this is what it does. So if I check my y variable over here, I'm printing my y. So you can see like it has given value 0, 1, and 2. Okay, got it?
Yes, sir.
Okay, great. So this is how like you do, you change your categorical column into a numerical column. Okay. So this basically helps in like feeding to the model to actually train on. And this part, like I am scaling my data to a similar range so that my model should be not biased on any of the variables. So basically you can see like I have scaled this data, my input features, to a very smaller range, and all the features actually lie in the same range. Okay, so let's
Is that similar to normalizing the data?
yeah, it's normalizing the data. Here I am using just the standard scalar method to normalize the data. So there are a lot of other methods also, like robust method and some different methods people use actually. This is the very basic normalization technique. Okay. So next step in my slide was to calculate the covariance matrix. Okay. So this particular function. Yes, someone has some question. Okay. So the next step was to calculate the covariance matrix. So here you can see like I have calculated the covariance matrix. So I am using this thing covariance function of numpy. So this actually gives me the covariance matrix of the this thing. So basically, what covariance function actually, I am transposing the x variable. So what I am doing, I am basically converting the rows into columns and columns into rows. So basically, my this particular part x dot t. So it's a property of a numpy. So if I say array dot t, it will transpose the array. So basically what will happen, like I will have from this uh, currently, like in my X, what is there, like I have 4 columns and 150 rows. So 4 columns and 150 rows. So if I do x dot t, it will become 150 columns and 4 rows. So basically my covariance method actually needs samples in a columns. So basically that's why I have to convert the X matrix into like I have to transpose that matrix. So here it gives me the covariance matrix. Okay, so as you can see, these are the covariance with respect to the same variables. So you can see this is basically the covariance of sepal length, comma sepal length. That means sepal length with respect to itself, and this is sepal width with respect to itself. Okay, so these are like the covariance with itself. Now, if you'll see this particular thing, this has a negative covariance. So what does that means? Basically, like the sepal length has a negative is negatively correlated to sepal width. So let's do a graphical representation of this covariance matrix. Okay, so I just executed this particular cell, and first I will explain you the code in the cell. Okay, so now my covariance matrix, I know that these are the columns. These are the columns for which I have the covariance. So I have just declared a list of columns. So my first is column is sepal length, second column is sepal width, and actually this is used for labeling in my graph. So I want to label this part, right? So this sepal length, you can see sepal width. So it's coming from this particular list. Okay. So I'm using PLT. So I have actually imported the library matplotlib as PLT, right? I have given the alias as PLT. So I'm using that library PLT.figure. I'm specifying the size of the figure. So 10 by 10 means like the 10 inch by 10 inch size of my library of my graph of my figure. Okay, then I'm just setting up the font scale, and here I am like drawing a heat map. So basically for the heat map to draw, I have to provide the covariance, I have to provide the data. So whatever covariance matrix I have given that data to my heat map, and these are some of the properties of that heat map method, wherein I can say a naught and square, true, and this is a font family, like font size and all those things. So and X labels, I am like providing the X for X labels, and Y labels, I am providing the columns false variable which I have in the list in the form of a list. So this columns will get printed on my x-axis and y-axis. Okay, this is the title, and this is some of the property like type layout. So you can just go through that, and as soon as I say dot show, it will draw the graph on my screen. Okay, so as you can see from this particular graph, like this will show me the covariance between my features, right? So this you can see like with the light color, these are having all covariance as one. This is basically it's a covariance with itself, right? And which are of the black color, those are highly negative correlated. So basically petal width is highly negatively correlated with sepal width, right? And petal length is negatively correlated to sepal width. So this is how like covariance matrix actually gives you the correlation between your data sets, between your features, right? uh, I want someone to actually explain me like what I have explained right now. So can someone volunteer themselves? Like I don't want to pick up someone and do that. Guys, come on.
Hello?
Pardon?
Hello?
Yeah.
Yes,
Who is this?
can you, sir, Vandana here, can you show the code again so that I can explain?
You are not audible as such, so
Yes, am
it's
I
not
audible
clear.
now? Am I
Yeah, yeah,
audible?
yeah, yeah.
Yes, can you explain? Can you show me the code so that I can explain?
Yeah, yeah. So explain it from here. I want you to like explain it from here in the graph.
Yes. So here you have calculated the covariance of sepal and sepal with petal width and petal width. First, you have calculated the transpose of it. So 150 rows will be converted to 150 columns, and then 5 columns will be converted to 150. 5 columns will be converted to 5 rows.
Yes, yes.
Yes.
And
Next, here, graphical representation of the covariance matrix using a heat map. So you have
mhm,
created a list of the names, sepal length, width, petal length, and petal widths. Then you have decided the size, which
yes,
size you want. So it is 10 by 10,
good.
a kind of
Yes,
matrix.
yes, yes,
Then it's a font scale, 1.5 that you have selected, and then
yes.
to heat map method, to heat map function, I think so it's a function to draw this graph matrix.
Yeah, it's actually
So
like configures your graph. Yeah, yeah.
so
Good.
to
Great,
this
good.
you have provided this variable which you have calculated earlier, cov, that is covariance, and then annotations too, because we want to give the annotations to it. Then something I can see, what
Yeah,
is this point?
these are random properties, so just forget about it.
Yes, yes, yes.
What does this
Yeah.
y-tick labels and
So
x-tick label does?
it will give the labels on the x-axis, sepal length, sepal width, petal length, and petal width. So this horizontal and vertical that we can see the labels here,
Yeah,
here on the
yeah,
graph. Yes. So these
yes,
are
yes.
the given by x-t cables and y-t cables. It is taken from that list which you have written earlier. Call equals to,
Odds.
yes.
Yeah,
Calls
good,
equals to.
good, good,
Then
good, good, good.
yes, then you have given the title to this graph, covariance matrix showing correlation coefficient, and then type layout, and then plot dot show is used to show.
Yeah, good, great, great. So as you have seen, like we have done like we have completed the first step of standardizing the data, normalizing the data. Second step of like calculating the covariance matrix. So third step of my PCA calculation is like calculating the eigenvectors and eigenvalues. Okay, so there is another method in my NumPy library, which is linearalgo.eig. So basically, this will give me the eigenvectors and eigenvalues. So I just ran this particular cell. Okay. And what I'm doing over here, I'm just transposing the eigenvectors to make my calculation easier. So I'm printing over here my eigenvectors. Okay, so these are my eigenvectors and these are my eigenvalues. So these are my respective eigenvalues, right? So over here, if you'll see the eigenvalues having eigenvalues, like the first eigenvalue is the highest eigenvalue compared to like second, third, and fourth. So from here, like I can assume like my first two principal components will be of the higher significance, right? So this is how you calculate eigenvectors and eigenvalues, right? So usually like here right now, like I have just four features. So it's a bit easy to actually see like which eigenvalues is higher and those things, right? But assume that we have 10,000 of features. So in that case, like what you have to do, basically you have to sort the eigenvalues in a descending order, right? So my arg sort function, so this is a numpy arg sort function which I use on my eigenvalue. So what does this do? Basically, this takes the list, so basically this array, okay, and it will actually return me the indexes of the array in the ascending order of the value. And then I'm doing, like I'm slicing this list in a reverse order, right? So colon colon minus one, this will actually go in a reverse order. So I'll just explain you how this works, right? So basically, let's say I have this eigenvalue. Let's say I have eigenvalue. Let's say the first value is like 50. Okay. The second value is, let's say, 60. The third value is, let's say, I have 20 and 10, right? So the what arg sort method will do, basically, it will return me the list of the IDs based on the values, right? So 60 is the most highest over here, right? So it will return me first value in the list will be 1, right? Because it is of the index 1, right? So it will return me 1. Then the second highest is 50, right? So it will return me 0. Okay, and the third highest is 20, so it will return 2, and then the 3. So this is how the arc sort method will actually work on. So it will return me the list of indexes in the descending order, ascending order of their values. And then after that, what I am doing, I am saying like I'm doing an operation on the list, right? So you know, right, from this to this in the step of -1, right? So what it does, it will so sorry, this will be in ascending order. So my bad, it will be arc sort will return 3, 2, 0, and 1. And when I do this particular part, it will actually return me 1, 0, 2, and 3, right? So this is how it will work. So my arc sort function will return me the IDs in the ascending order, and when I do slicing, I'm moving from back to forward, right? I'm giving a parameter as -1, so it will return me 1, 0, 2, and 3, right? So this is how it will happen. So I'm just printing the IDs. So right now, my eigenvalues are actually in a descending order. So it's giving me 0, 1, 2, 3. So the order hasn't changed, right? Okay. So what I'm doing, taking this ID list of IDs, I'm rearranging my eigenvalues and eigenvectors. So what I'm doing, basically, I'm saying eigenvalues and I'm passing this IDs, right? So what it will do, zeroth index eigenvalue will be shifted to the first place, and so on. Like first index where one first index will be selected on the shifted on the second page. So this is how I am actually sorting my eigenvalues and eigenvectors, right? So over here, I'm just printing my eigenvalues and eigenvectors again. So I can see like top two eigenvalues has a higher number. So I can assume like my first two principal components can represent my whole data. right? So what I am taking, I am just taking first two principal components, first two eigenvectors. Okay, so from this I know like first two eigenvalues are more important. So I'll just take two eigenvectors out of it. So these two eigenvectors I can consider from the array, and I can consider this as my principal components. Okay. Now the data which I had in my x variable x. So what I am doing, I have to now compute my projected data. So based on those two eigenvectors, I have to project my x data, right? My input features. So what I do over here basically is, this is a 4 by 2 matrix, right? So and my x data is basically, x is basically uh, 150 by 4, right? So to actually make the matrix multiplication, I have to transpose this particular matrix into 4 by 2, right? Then only I can multiply it. So basically I'm doing a dot product of x and transposing p components, and that's how I am doing a dot product of a matrix, and that's how I get my new features. That those are x projected features. I'm storing it in x projected feature. So as you can see, like I got two features out of that. And if I see, if I print the shape of those two features, those variables, like I can see the old variable has a shape of 150 rows and 4 columns, whereas the new transform feature has a row of 150 and 2 columns. Okay. Mm, so anyone can just volunteer like what I have explained till now. Can someone? Can someone else try it out? The fourth step of just explain me the fourth step of eigenvectors and eigenvalues, like how I am deriving eigenvectors and eigenvalues. Can Pooja Mehta? Can you explain me? Can you try, Pooja? Or Varsha? Can you explain? Guys, if I will keep on talking, that I don't know like whether you guys are understanding me or not. Like, so that's why I'm making like people to actually explain me. Like, are there some issue going on? Like, because I can see a lot of chat messages. Can someone reply? Apeksha, can you just reply?
So there is a problem with the feedback form, feedback from attendance form. So that's the reason participants are sending the messages in the chat.
Oh, okay. Okay, so should I actually go ahead and explain to you the rest of the stuff?
Yes, sir.
Okay. Okay.
Yes, sir, you can explain us. We are listening to you.
Okay. So here we actually reduce the uh, features, reduce the dimensions from 4 dimensions to 2 dimensions, right? So here we have like x projected features, So we have checked the shape of the X projected variable, and it's like we have reduced from 4 columns to 2 columns, right? So if I take those 2 columns and if I see a graphical representation of those 2 column principal component 1 and 2, it clearly sees that like it helps me in like visualizing the data, right? It actually represent my whole data. The instead of like representing by 4 features, I can just represent by 2 features, and it clearly like categorize my data into 3 categories like Setosa, versicolor, and virginica, right? So again, like I am like drawing in this cell, what I am doing, I am basically taking the first feature from my X projected variable. So I'm saying all the rows, that is like this, colon and comma, zeroth column, right? So I'm saying all rows and zeroth column. I'm taking the first column values in X1 and the second column value. So I'm taking all rows and I'm giving an index 1. So always index starts from, in Python, starts from 0. So basically this is my zeroth column. This is my first column, right? So I'm taking that in a variables called x1 and x2. So this scatter plot actually accepts parameter for x-axis and y-axis. Okay. So on axis I am providing x1, and on y-axis I am providing column x2. Okay, and here like I am this why I have the species in that, like initially when we separated out the output parameter, we have like 0 1 2 0 for virginica, 1 for versicolor, and 3 for 2 for virginica, right? So these I'm using to actually color my scatters, to color my points in the graph. Okay, and this is the color palette I'm using. So basically you can use whatever color palettes you want. And alpha 0.8 means I'm using a transparency of 0.8 basically, like and these are the, as I explained, like these are X labels and Y labels, and these are the labels which I'm printing on X axis and Y axis. Okay, and color bar, this is a color bar on the side of my graph, which it appears. And I'm saying dot show method. So basically it shows the principal components graph basically. So over here, like we can just see that like it has well classified my species by using only 2 principal components. Okay, so this is how like PCA is done. So basically this is how we do from scratch. So we calculated, like we standardized the data, we calculated the covariance matrix, we calculated the eigenvectors and eigenvalues, and then we moved ahead and we did finding the principal components and then reducing our dimensions, right? So the other way actually to do a PCA is using a library called sklearn. Okay, in the sklearn they have a pre-built method or pre-built object called PCA. So what you can do, you can just import the library, PCA library, and you can import the PCA library from sklearn and create. Here I am creating a object of PCA, and then I am actually feeding the data x variable wherein I have the data of my input features, right? So if I execute this particular cell, what I can see basically is, so here I have not specified the number of principal components, right? So what happens is it will actually return me all the 4 principal components. So as we have discussed earlier, so the number of dimensions actually represent my number of principal components. So if you have 4 dimensions, then the principal, you can calculate 4 principal components, right? So these are my 4 principal components which PCA object has actually derived from my data, from my original data, right? So in the above code, we have seen that we have created a PC object. We did not specify the number of components in the constructor. Hence, all four features has been displayed. Okay, so now PCA object has a property called explain variance ratio. So here, what it does, it actually tells you like how much variance each principal component has. So you can see from this particular list, this particular array, that the first principal component has 72% of variance. My second principal component has 22% of variance. Okay, and my third principal component has 3%, and this though like having less than 1% also. So from this we can actually derive that the first two principal components will constitute of 95.81 percentage of my classification information. So basically 95.81% of variance has been observed in my first two principal components. So this is how you come to know like, okay, only first two principal components are more useful, and then I will plot a scree graph, cumulative explain variance graph, wherein like you can see like so basically my explain variance ratio, it returns a list, right? List of array. So basically what happens is that this actually is the zeroth, as is at the zeroth index. Hence you can see here in the graph like at the zeroth point it is 72%. So it has somewhere the point is at 72.96%. Then as you increase your PCA, second principal components, you add the variance, it goes above 96%, right? So this is how like plotting a graph, this is how you can know. So after second component, third component, it's like highly like it's very limited variance. So we can just consider these two principal components to actually represent our data. So this is how principal component is done, right? Uh, Guys, can anyone volunteer and explain me the last part of the CA?
Sir, I have one doubt.
Yes, tell me.
Instead of using the other method, the earlier method, can you just go with the sklearn method because already
Yes, yes,
inbuilt PCA is there.
yes. You can go with that. That will be
And
much more. It will be much more better, and like it will be. It gives a high this thing also. Like it's optimized also. So basically, the concept behind like explaining the first method was like to know the concept behind the PCA. So that's what the whole
okay,
funda actually.
okay. So the answer getting by the first method and directly using the
Yeah, you can
sklearn
you
PCA is different, right?
yes. So you can
Okay,
directly use the library, SKLearn library, to do the PCA.
okay. Thank you, sir.
Okay, can anyone explain what this explain variance ratio does? Uh, Vandana, can you explain me? Vandana, hello.
Yes.
Yes.
So,
Can you
am I audible?
explain? Yeah, you are audible.
Yes.
So can you
So
explain me this part?
yes. So it will return the variance caused by each of the principal components.
Okay. So what conclusion can you make from here?
It is responsible for 72.96% variance.
So basically, the observation which you get from here that the
First
first
principal component is responsible for 72.9. 96% variance.
72.96% of variance, and the second
Yes.
is responsible for
22.85.
yes.
22.85.
And if you give both, if you take both these principal components, then
It's
they will actually.
95.81. Yes, they will be added.
So this means like you can represent your whole data of iris flowers with these two components itself, right? You don't have to
Yes.
provide all the four features to the machine learning part.
Yes.
So anyone have any question regarding PCA? First, let me ask, like, did everyone understood like what I was explaining? Okay. So Tanuja says yes. Good. So, so the second method, the second technique for uh, feature selection, I will just introduce do some introduction part because I think it's almost time is like 6:50. So just 10 minutes left. So in that time, like I can just explain you the fundamentals behind the LDA part. Okay. So LDA is another technique of features extraction. So basically, LDA it's most likely like a PCA only, but PCA actually focuses more on variance in the data set, right? Variance in the principal component. So PCA, what it does basically, wherever it sees like the data is the variation is variance is higher, it selects actually those principal components, and it considers that those principal components has the highest information, has more important information. But LDA, in contrast, what it does basically, it maximizes the class separation. So basically. It will actually do a feature extraction based on the classes, and it's a kind of like a supervised learning. So what it means basically, it actually needs the classification first. So if you want to train your this thing algo, linear discriminant analysis, it's basically needs a it basically needs the output parameter also. So in the earlier case of PCA, as you would have seen in the code itself, like we didn't provided the y, like the in the flower, this thing, we didn't provide the species column to the PCA to actually do a feature extraction. But in case of LDA, you have to provide the species column as well to actually do the feature extraction. Okay, so LDA is a supervised learning, okay, which I have already explained. So it tries to find components which separates the classes the most. So it actually focuses more on class separation, as you can see from this particular diagram. So basically it will draw like imaginary line, like basically an axis wherein like two classes can be separated very well, right? And LDA is used where we're very interested maximizing the separability between two groups so that we can make the best decision. LDA is more like PCA, but it focuses on maximizing the separability among known categories rather than focusing on variance. Okay, so this is basically a difference between PCA and LDA. So I'll just give you a bit like a small example, like wherein like what's the difference in PCA. Let's assume like I have these points in my graph, like a green groups and a red group. Okay, if I draw a line in such a manner in this second graph, you can see that the class separation is not well, but the variance is very high. So PCA will consider this as my first principal component. But in case of LDA, what it does, it actually focuses more on grouping it. So basically, it will, if you draw a line in such a manner, you can, and if you plot all these points like in that particular line. So let's say I'll just take this. So let's say I have if I draw a line over here, okay, what it does, if I plot these points on this particular line, so this will actually give me the high variance in the data. It will actually focuses more on the variance of a data. But if I draw a line somewhere here, and if I project the points on this particular line, so what happens, the it will give me a good separation of the classes. So what does that means? Like you can see from the figure, like the green dots, if I projected on this particular line, will be highly separated from the group, red red groups, right? So basically, you can see LDA is more likely used in like group classification or like classification problem. Okay, so so it's similar to the PCA thing, and the only difference is like since it maximizes the distance between the group. So basically, what it does, it actually minimizes the distance within the class. So basically, all the points of the particular group should be like near to each other, and it maximizes the between class scatter matrix. That means like the different groups should be far more separable, far more separate from the first group. Like two groups should be far more separable, and points within the group should be nearer. So what it does basically, it minimizes the within class scatter matrix, and it maximizes the between sorry, it maximizes with minimizes within class matrix, and it maximizes between class matrix. Okay, and so on top of that, like we calculate similarly as we calculate the eigenvalues and eigenvectors for PCA, we do this kind of computation wherein like we take the inverse of within class matrix and dot product of a between class matrix, and we compute the eigenvectors and eigenvalues of that particular formula. And this is how basically like LDA actually works. So I think I will just conclude the day for today basically, and we will see the coding aspects of the LDA. I think tomorrow we can see that also. Is it fine?
Yes, sir.
Okay. So I think we can just conclude our session for today here. So tomorrow we'll be like doing a demo code for LDA, and I will be also discussing the other technique that is singular value decomposition. And there is another topic of like how to deal with minority data. Like if you have a less data of a minor class, how to deal with that, like oversampling and undersampling. So those three topics like I will be covering tomorrow. Okay, so I would like to have a general feedback like from you guys. Like, so I have been talking and talking and talking. So I don't know like whether you guys explain whether the speed is like fine to you. Like, how am I explaining? Is it fine? Yes, I need some feedback. Anyone can give me the feedback. Any random person from the group can give me the feedback. Okay, tell me like the speed was okay,
Yes, sir. Yes, sir. The speed was okay, sir.
right? So okay, and uh, general feedback about the session, like was it informative? Okay, So people tell, okay, very informative. Thanks a lot. Thanks for the feedback. So what we can do, like we can meet up tomorrow again at 5. Okay. So we'll see what LDA and SVD are, and we can actually do some kind of oversampling and undersampling, and we can see how we can deal with different type of data. Okay. Thanks. Thank you, everyone. Have a good night and take care. Okay. So I'm just signing off. Yeah, do you have anything?
Thank you. Yes, thank you, sir, for wonderful session on
Thanks.
coding dimensionality reduction in Python using PCA. That was indeed a great session, sir. Thank you so much.
Thank you. Thank you. Thanks a lot. Okay. Bye.
Thank you,
Bye, everyone.
participants. Thank you for your patience listening. Thank you.
Rathod sir, are you there?
हा मॅडम, हा मी आहे. प्रमोद सरांशी फोनवर बोलतो.
Okay. Okay.
जस्ट अ मिनिट. हा सर बोला.
Participants, you may leave the session.
येस मॅडम.
हा सर.
थांबा एक मिनिट. हा ते
हो.
ऍज युजल मलाच करावं लागेल ते काम.
प्रमोद सर पण आहेत, देवाडकर सर पण आहेत.
प्रमोद सर कुठे आहे? प्रमोद सर फोनवर बोलतायत. माझ्याशी बोलते
होते
आता.
आता.
अरे जस्ट अ मिनिट. स्टॉप द
वर्षा मॅम आल्या का? नाही आल्या.